Hello everyone, my name is David. I represent the group that published the paper Training Ensemble of Quantum Binary Neural Networks. My co-worker was Tiago de Lima and my advisor was Adenilton da Silva. In this presentation, we will follow this roadmap going from objectives, motivation, introduce concepts of quantum computing, show some related works, explain the hybrid quantum technique used to create this paper, then explain the ensemble technique created, compare the results, and discuss the conclusion. The two objectives we came up with are enhancement of the QBNN proposed by Ahmed Fawaz and the creation of a technique that solves the amplification problem found on the QBNN solution using less computational cost. Artificial neural networks require tedious and expensive experimentation for tuning neural network parameters for a specific dataset. Also, heuristics to optimize neural networks parameters have been proposed in the last 20 years. On the other hand, quantum computing is a growing research field. Also, quantum parallelism is inherent to quantum devices and allows us to compute the output of a function for different values in superposition with a single function call. A quantum bit or a qubit is a quantum information unit that can be represented by a bidimensional vector. Cat0 and Cat1 represent orthonormal vectors. Cat phi represents the state of the qubit where the sum of the modulus squared of the amplitudes should be 1, due to conservation of probability. A quantum gate is an operator that acts on a number of qubits and it's represented by a unitary matrix. Examples of operators used in this presentation are as follows. The X gate flips the state of the computational basis from 0 to 1 and from 1 to 0. The Hadamard gate may create a superposition of different states, and finally, the RY gate is a parametric rotation about the y-axis of the Bloch sphere that depends on theta. Finally, a quantum circuit is a model for quantum computing that represents a computational as a sequence of gates acting on a set of qubits. On the figure, you can see a circuit and the corresponding measurement probabilities. Similarly to a binary neuron, a quantum binary neuron has its inputs, weights, and activation function. In this particular case, the multiplication is described as an open controlled operation having weight as controls and inputs as targets. The activation function is a common majority function described by Ahmed Fawaz. The quantum binary neural network, equivalent to a binary neural network, has its neurons, inputs, layers, and outputs. This specific case has the inputs initialization on the first layer. On the hidden layer, two neurons have their weights for each input and the majority function as the activation function. On the last layer, the neuron that produces the output has the same structure. The first circuit on this slide represents the procedure to generate one output, and the second circuit represents the feed-forward step of the QBNN. To evaluate this QBNN, we use the same type problems proposed by Ahmed Fawaz that are described by the functions. The first function receives three parameters, multiplies the third by the first, then sums with the second and applies sine function. The second function sums the three parameters and applies the sine function. The sine function returns 1 if the input is major or equals to 0, minus 1 otherwise. With these functions, we will build our dataset. Groove's algorithms performs a search on unstructured data with computational cost O square root of n and has no counterpart on classical computers. To train the QBNN, Ahmed Fawaz uses groove amplification to search for the best combination of parameters after performing all the feed-forward steps. The problem of this technique is that we have to know the maximum accuracy the problem can hit, and at each amplification we need to check the output, and if the accuracy wanted is not reached, the procedure needs to run all over again from the first amplification. To achieve our first objective, the main change needed was to remove the multiplication and load the inputs directly on the weight, then apply the majority using the weight. We also removed the qubits used to store the outputs of the hidden layers and applied the majority function onto the weights of the last neuron. That way, we reduced the amount of qubits used and the depth of the circuit. Variational quantum circuits are a hybrid optimization algorithm. Here we have three steps. Step preparation to encode the input data. The model circuit, a parameterized unitary transformation to train that generates the output state. And at last, the readout qubit, a measurement using a Pauli operator will give us +1 or a -1 value. Using the variational quantum circuit approach, we were able to improve the previous method. First, we modified the way to generate the superposition. Instead of using a Hadamard gate, we apply a RY rotation to create an ensemble of QBNN, controlling the superposition. That way, instead of creating an uniform distribution with Hadamard gate, using a RY gate, we create a controlled distribution to increase the probability of having the best weights combination. Then we have a new method to train the ensemble. Instead of using grooving amplification, with the output generated, we check if it hits the correct value, then compute the loss, and finally update the weights to load them using another input and do it until we hit the expected accuracy. We decided to optimize the circuit using a conventional and well-known optimizer, Adam and Adagrad, which has shown that finding the fittest weights is possible. We accomplished the same result solving the problem we had with groove approach. This graphic, on the x-axis, we had the epochs. Each epoch on groove means the whole feed-forward step and one optimization. The hybrid approach means 8 optimization for each input, resulting in one feed-forward step. We show that the groove amplification has a problem of not knowing the number of amplification needed and if the expected accuracy can be reached. We accomplished the two objectives proposed here, and for future works we have some proposals: loading bigger datasets, checking if the weights and architecture selection are most suitable with heuristic methods, and also finding a way to load real or complex inputs. Our acknowledgement go to three government organizations that finance this work. Thanks for watching. Our contacts are described here, and have a nice event.